open up another P program. A bar magnet lies horizontal. Okay. A bar magnet lies horizontally on some paper, which is also horizontal. A magnet lies on the y-axis with the north pole on the positive y. Okay, so here you can think about it like this. I'll draw a table. And you had a piece of paper on it. And I said the north pole is up here along, I called this one y, and this one here would be x. And I put a magnet lies on the y-axis. Oh, sorry. Yeah, no, that's right. The magnet lies on the y-axis so that the north is up the top end of it. Like this. North is there. And an electron moves along the positive x-axis. So an electron is moving along here. So it goes along here like this. So the magnetic field is going around like that. So if I kind of draw it now from the top to be a little bit clearer, here's the magnet, and here's the electron moving across like that, and the magnetic field is going down like that. And my question is, which way is the force? So which rule is this, left or right? Left. Now, where do I put this finger for the field? Down. Yeah? Which way do I put my current? Left or right? Ah, gotcha. Left. Because it's an electron. So which way is the force? Outwards. Outwards, yeah. Yeah, so the electron will feel a force outwards. Is that okay? Continue. Question, Siba? Question? Are you sure? Kim? No, continue. So, next one. A magnet has a flux of 400 milliwebers. Milliwebers. Over a square of length 2. What is the flux density? Okay, so flux density, remember, is flux over area, which is 400 times 10 to the minus 3. And what's the area here? It's a square. 0.02 squared. Alright. Siva, could you hit that in a calculator? Let's see what we get for this one. Exactly 1,000, huh? Tesla. Okie dokie. Continue. 3. An electron moves perpendicular to a magnetic field of flux density 500 millitesla. What is the force if the speed is that? Okay, so you have a field. Let me draw it here. We'll keep it easy. We'll just make the field come out of the page. So the field is heading towards you, and it's 500 millitesla. And then an electron enters the field, and it'll experience a force. The electron is travelling at a speed of 0.01 c. Now, I want to make sure you guys know the left and the right hand rule. So I'll give you about 10 seconds. I want you to tell me which way the force will be on the electron. So, left or right? Left, okay.
Why left?
Because you're trying to... basically, you use right hand when it's generators and left hands when it's a force, a magnetic field being applied to a charge to make a force. Got an answer? Right. Which way is the B? Which way is the magnetic field density? The B. Which way is that? Up, down, left, right, in, out? Out. I just drew it there, see? Coming towards you. Okay. Which way is the current? Which way is the current? Which way is the current, left or right? Left. Because electron is headed to the right. So which way is the force? Up. So what will happen is, as the electron enters the field, it'll experience an upward force. Oh, it's hard, isn't it? Too much visualization. Right, well, do you remember what the formula is to calculate this force, the electron fields? QVB. So that's charge of electron times speed of the electron times B. So let's bash this into the calculator and see what we get. The force is actually pretty small. 2.4 times 10 to the minus 13 newtons. But I guess because it's only an electron, it's actually still pretty big. That was number 3, wasn't it? Yeah? Next one. I make it look easy, I'm sure. Continue? Yeah. Okay, next one. So, what's happening here? A particle of mass 10 to the minus 25 kilograms and charge of minus 2e is moving along. It enters a magnetic field. How big do I say the field density is, please? 750 millitesla. Now, this is exactly like the last question. I mean, the numbers are different, but it's a negative charge moving right into the field, which is heading towards you. So what way will the force cause this to move? It'll cause it to move up. Okay? In fact, it'll actually move in a circle. And my question is, what is the radius of this circle? Now, we're getting interesting. So, do we know how to calculate the F here? We do. The formula is Q V, or what did I say the V was in this question, please?
0.05.
Speed of light. Yeah. Q V B equals. Right, I'll let you type this in for a change now, since I did the last one. So tell me what the force is here. It should be kind of small again. 10 to the minus something newtons. Who has any ideas on how we could calculate the radius now that we know the force? I'll give you a clue. It's moving in a circle. Circle.
E equals 1 over 4 pi.
No? Okay, remember circular motion, you have the formula F equals mv squared over r for circular motion. Do you remember this from circular motion? Now, come on, everybody look up since nobody remembered or nobody saw this. Do you know the F? Yes. Do you know the M? Yes. Do we know the V? Yes. We have it here. So could we get the or? We could. So the or is just going to be mv squared over F. We know all of these things. So the m is 10 to the power of minus 25. The v is 0.05 times c. And the f is 3.6 times 10 to the power of minus 12. So it's a 6.24 meter radius. No. No, because it's in a field between yeah, that's only if it's a point charge field. But this field is actually like almost like parallel plates. Is that okay? You understand you'll be taking an exam in a few months that tests all this, right? So if it's not okay, you need to say something. Yeah? See that? Kim? Is okay? Is that yes or no? It's hard. It's very hard. You need to maybe practice some more at home. Maybe you could try and solve them again, see if you get the right answer. Will I go on to number 5, the last one? This one here is actually it's a pretty common exam question. This one here. I've seen it a few times in the exam. Seen it a few times. Right. Next one. Great. 5. Okay. You've all done mass spectrometer in chemistry, haven't you? You studied about this machine. Shown below is a mass spectrometer. Firstly, a sample is heated up and becomes a gas. Can you see that in the picture, stage 1 of the picture? Do you see that heater? Yeah. Then electrons are fired at it so that an electron can be freed. This is the ionization chamber. Yeah? And so this makes the gas positively charged, stage 2. This charged particle enters an electric field and is accelerated up to a great speed, stage 3. So do you see stage 3? You have 2 electric plates. This causes the particle to accelerate. Okay. The charged particle enters an electric field and accelerates. The particle then enters a magnetic field which causes it to move in a circle. So do you see that last question we did? When it enters a magnetic field, it will move around in a circle, as shown in the picture. The particle then enters that's stage 4. And finally, strikes the detector at some location in 5. Now, can you see, I don't know if it's quite clear, but can you see if the radius is too small, it hits the wall. If the radius is too big, it hits the wall, but if the radius is just right, it'll hit the detector. Can you see that in the picture? See the way, like, if it's too small or if it's too big, it doesn't come out. Now, can you see here, if the radius is bigger, it will hit the detector. Can you all see, guys? Look at me. If the radius is bigger, it'll hit the detector to the right. If the radius is smaller, it'll hit the detector to the left. So actually you can, from where it hits the detector, you can know what the radius was. Okay. So let's have a look at the questions now. Part A. Let M represent the mass, Q represent its charge, V the potential difference between the plate and stage 3. Find a formula for V, the speed of the molecule as it leaves the plates and enters the magnetic field. Okay, so let's have a look at the picture. Here's stage 3. And the particle, you know, maybe there's like a little hole in the plates. So the particle enters and then accelerates and then comes out the other side. We can just use the formula we've been using, potential energy equals kinetic energy. So what's the potential energy here? That is Q E D. That should equal a half m v squared. What's the formula for E? That's voltage over D. So actually they cancel down. So 2q times the voltage over the mass, that's equal to the velocity when you square root it. So that's the answer for part 1. That's how quickly it will leave stage 3 and enter stage 4 in the mass spectrometer. So that's root 2q, the voltage, over m. Okay. Can I continue? Do you have that part? Yep, okay. And then part B, stage 4, it enters the magnetic field, and then I want you to calculate the radius. Okay. So look, here's your particle, comes along, enters the magnetic field now. It'll move in a circle. We can use the same trick we did earlier today. You can say F equals Q V B. Now, the Q is Q. The V we worked out from the last part. What was it? Square root 2QV over N times B. Yeah? So I actually, I want you to find the radius. So now we need to use the other formula, F equals mv squared over r. So you can make these equal. So now you get mv squared over r equals q root 2qv over m times b. And I'm looking for the radius, so I'm going to have to rearrange this now. Okay. Can I scroll down a little bit? Yeah. So rearranging, I get the radius will equal mv squared over qb root m over 2q voltage. I'm accidentally doing B and C at the same time, really, so. Okay. Right, continue. Continue? Yeah. Okay. sec. I'll just check something here. All right. Actually, before we continue, is there any simplifying we can do here? We could kind of clean this up a little bit, couldn't we? Because you have M's you can put together and Q's you can put together. But for the moment, maybe I'll just leave it. Right. Hence, find a formula for M over Q in terms of V, or, and B. All right, okay. Let's clean this up a little bit here. I want to get rid of the square root, so I think I'll just square everything, okay? So I'll get R squared equals M squared. Oh, sorry, I'm not quite finished this. Just to be clear, that's voltage and that's speed. So I need to sub in what the speed is. Can you read out what the speed was? What was it I got earlier? Square root 2qv over m. No, I'm done. Have I done something silly here? They're going to cancel, aren't they? Oh, it's getting messy. Yeah, no, that's okay. Yeah, no, sorry, that's okay. It's just a messy question. It's difficult. Okay, so here I get R equals M2Q voltage over QB root M over 2QV. Goodness sake. Okay, what can I cancel here? What can I cancel here? I can cancel Q, M. Anything else? No. I want to get rid of the root, so I'll square everything now. So R squared equals 4 voltage squared over B squared M over 2Q voltage. Okay, I can cancel voltage again. Cancel. Anything else to cancel? No. R squared equals 4 voltage M over 2QB squared. Okay. If I rearrange this, I can get M over Q equals 2B squared R squared over 4V. So I can get M over Q equals B squared R squared over 2V. That took a heck of a long time to do. It was very hard. Okie dokie. Finish that one. Now, why bother doing all of this? Well, you know, one thing about the mass spectrometer is that you want to work out the mass to charge ratio. Yeah? So, mass to charge ratio equals B squared over 2V times R squared. Now look at the things that you know. Do you know B? Well, you do, because it's for the magnet that you're using. Okay, so you know this. Do you know the voltage? You do, because it's your machine. You know what the voltage between the plates are. You can measure this when it hits the detector. So it's easy to calculate this, and by calculating this you can work out the mass to charge ratio. This is how the mass spectrometer works. The mass to charge is actually proportional to the radius squared. I don't know if you do any formulas in chemistry for it, do you? Were you at least told a bigger radius means a bigger mass to charge ratio? You were at least told that? Okay, that's good. But you weren't told the precise relationship. The precise relationship is this. So, oh man, yeah, okay. Don't worry, it won't be that hard in the exam, but please, questions 3 and 4 are definitely exam questions. Okay, what class have we got next? Easy peasy? What are you doing? Integration by parts. Yeah.